Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So the title actually has a question mark at the end. Okay, so it's not, I'm not stating that it's going to be the default machine learning platform. All right, so my name is Milind Bhandarkar, and in the last 20 years of my career, it has been split into basically roughly two parts. First half has been focused on HPC, and the second half has been focused on what we call as the big data now, although I do not like that term at all, because then the next question is, okay, how big is big, right? So I don't want to answer that question. One thing to note about my profile is that I have absolutely no experience in machine learning, which basically makes me the perfect candidate to speak at a distributed machine learning workshop. But anyway, just a few people to acknowledge. Of course, this is not my own presentation. It's been collected from various people. A lot of open source development has gone and based on a lot of proprietary work that has gone on in building distributed data platforms. A lot of ex-colleagues to thank at Yahoo Research, who basically provided me with a lot of input on how they do machine learning on this fledgling platform at that time in 2006 called Hadoop, and that has improved the platform a lot. A lot of my colleagues at my current company called Pivotal, who claim to be data scientists, another word I do not like at all, sort of a commercial term, right? And most importantly, Vijay Narayanan from Microsoft, again ex-Yahoo, who and I actually, he and I conducted a tutorial on doing machine learning using MapReduce at KDD 2011, and that prompted me to go over this entire survey of different machine learning techniques and how they were implemented on top of MapReduce. So just to clear some confusion about where I am from, because the program says I am from Greenplum EMC. So yes, I used to be in Greenplum EMC, and my division has been now spun off into a new company, a new startup called Pivotal. So that's where I'm from, mainly focused on Hadoop though. So I've been with the Hadoop community for almost since its beginning. Actually, I joined Yahoo in 2005 to revamp its search infrastructure, and what came out of that is essentially Hadoop. So this is the actual picture of the first Hadoop cluster. We actually had borrowed 600 machines from our Yahoo search engine people who were going to throw it away or sell it on eBay or something like that, and basically said we are going to run this new platform called Hadoop on top of that. And when I left left Yahoo in 2010, we had more than 45,000 machines containing 300 petabytes of data. You know all the numbers probably already, right? So it has been a huge success. In the meantime, we had a very nice 500 machines cluster, literally sitting in a trailer outside of the Yahoo buildings in a Yahoo parking lot, which we actually repurposed as an academic collaboration cluster. We actually had a lot of research done on that, mainly in the natural language processing area. Tom Mitchell's group in CMU actually used this cluster a lot. Observing their work actually gave me a lot of confidence that given some free software and free hardware, good research work will come out of it. Right? Okay. So I took that to heart. I basically, when I left Yahoo and joined Greenplum, now Pivotal, we established a partnership between various hardware vendors, and they donated a lot of hardware. So we set up this thing called Greenplum Analytics Workbench, now Pivotal Analytics Workbench. It's a 1,000-node cluster running Hadoop and other distributed data platform software. It's a full-fledged Hadoop cluster. It's a fully managed Hadoop cluster. You don't need to do anything. You just bring your data, bring your applications, get your research done. It's basically just fill up a form and we'll provide you the cluster. Okay, so that's all that I'm going to say about the clusters aspect of it. All right. So a lot of people have talked about and referred to Hadoop, MapReduce, etc. We all know when people say, you know, Hadoop is slow, Hadoop is this, Hadoop is that, people are mostly talking about, and I would say mostly, talking about Hadoop 1.0, which basically has MapReduce as the only programming paradigm supported at scale on this distributed systems platform. Okay? If you have to implement something else, well, you first do the batch processing using MapReduce. You take results of that data and then publish it somewhere else in order to, maybe in HBase, maybe in your relational databases, etc., to make it available to the real-time interactive queries, or just take a sample of that, load it into an Excel spreadsheet and do some plotting, visualization, take that data, load it into memory in an R program, and then do some interesting machine learning work, right? So that was Hadoop 1.0. Hadoop 1.0 limitations, of course, were that the system daemons that were supporting Hadoop, like job tracker and task tracker, were sort of hardwired with MapReduce as the only programming paradigm that they would support, right? They would not support, for example, peer-to-peer communication, an all-reduce-like communication, nothing like that. You had to have a map, you had to have a shuffle, and optionally we have to have a, so optionally you have to have a shuffle, and optionally you have to have a reduce, right? That was the only paradigm that was supported. But what happened is that since this was probably the only platform that was available at scale to all these machine learning researchers in Yahoo and elsewhere, they basically had no other choice but to repurpose Hadoop and MapReduce for their own work, right? So first of all, Hadoop has been optimized for data throughput. This whole notion of pushing computation to where the data is, and most of the times executing your map tasks close to where the data is already stored basically meant that you could scale your number of map tasks, and accordingly you could increase the bandwidth that was available to you. So 100 terabytes per hour processing all that data in a streaming manner from the disks using 500 mappers was sort of common, okay? The second thing, and this has come up again and again, is that the most useful feature of Hadoop, especially working on commodity hardware, is its fault tolerance, right? And I would say that the commodity tolerance and commodity hardware and failure of those components, hardware components, actually comes up again and again. It gets its more than the share, mind share that it deserves. Actually, it's not that the hardware components fail intermittently, right? Yes, they fail. There is about a 1% failure rate that we have observed, and especially because of the spinning disks that are there in every machine, those are the only spinning mechanical part. Those tend to fail very often. 1% fail over a month, right? But your job typically runs for maybe a day. How many machines are going to fail in a 1,000 node cluster? The probability is actually fairly low. You are all probability and statistics researchers. You should actually calculate this probability, right? It should be fairly low. I think the main issue at that time, at least, is that since these clusters are multi-tenant, your application is not the only application that is running on any node at any time. There are other poor programmers who have written their applications which take over the entire machine and kill your job. That's the biggest number of faults that we used to observe in a production Hadoop cluster. So fault tolerance not only to tolerate the failing hardware, but really the multi-tenant aspect of this cluster actually killing or taking over the resources from your job and making your jobs fail. That's the failures that we observed most often.
So
okay?
Did you call that preemption, or did you call that more like
it's not.
It's like just your resources?
Well, this was the problem was resource isolation, and problem still is the resource isolation. You can do good resource isolation if you are willing to pay the price for it. For example, you can nicely partition a single physical machine into a lot of virtual machines. And virtual machines with VMware, Citrix, whatever, these guys actually offer a very nice resource isolation that one misbehaving application inside a virtual machine does not kill the other application, does not take over the CPU, does not overflow its memory, does not take over the entire network by flooding it with 10 gigabytes of transfers a second, right? That was the main issue. And that is why when some of your code, in particular what we observed, but that the map task was not getting enough resources, the task tracker will believe that it is dead and restart that, right? So that's basically the whole thing that was happening. All right. And obviously excels in counting number of things, right? In fact, the hello world of MapReduce is word count, right? So counting is what MapReduce really excels. You have a question? Yeah. Yeah. Sure. Yes, absolutely. Absolutely. So in the initial days, I've been involved in running these clusters since Hadoop 0.1. In the initial days, the software was fairly immature, and in fact, we used to have a scheduled, unscheduled maintenance window once every 6 hours or something like that, right? And we won't care about other users that are running their jobs. We would just upgrade the cluster, and then we'll get an angry phone call from some user saying, I already have almost finished. Why did you reboot the cluster, right? But then later, as the software matured more and more, we used to have a scheduled maintenance window of 2 hours every week in order to carry out all those tasks. And we had redundant clusters in 3 different data centers. So we used to notify users in advance saying that this cluster is going to be down in the next next Wednesday or something like that. During this time, all this data is already available in this other data center in another cluster. You should go and use that. And then things, and most of the times now, this is how things are working. The whole rolling upgrade thing in Hadoop is still not there. Right? Okay. All right. It's built on commodity hardware. We have seen various customer cases who have replaced $20 million of Teradata equipment with $450,000 worth of Hadoop in AWS. So really, it has democratized the whole notion of again, I don't want to say big data, but just data processing. Okay, and since Hadoop and HDFS in particular offers a very cheap and economical way of storing this data, a lot of your company's data is already landing on this cluster and is already available. And given its scale, tens of petabytes of data on a single cluster is nothing to be scoffed at, right? I mean, so since it is already there, why can't we basically use this for machine learning as well? I mean, my manager at Yahoo, Eric Bolschweiler, who later went on to found this company called Hortonworks, used to have a saying in Yahoo search that I'm buying disks, CPUs for free, right? So already I have all these disks and storing all this data. These CPUs are just idling around, just doing some mundane replication tasks. Why can't I use those for doing some good computation, right? Okay, and in particular, when we are talking about machine learning, I mean, most of the advanced machine learning techniques, and especially when they are implemented in Java without giving any thought to CPU efficiency and how they are actually executing those instructions, they can soon become limited by computation, right? Not so much as data, because you are filtering out most of this data. You are probably throwing away a lot of this data. You are doing feature extractions in advance, and then after those features are extracted, those probably get the data sizes probably get a lot less. But then you have all these computations that you have to do on those, and then that has to scale across all these different machines, right? Okay. So what are techniques that people use to do machine learning in MapReduce, right? So the candidate algorithms that you have that were easily ported to the MapReduce model are fairly simple algorithms in terms of their communication patterns, right? Data parallel algorithms, it's a given. We are basically all shared nothing. You don't really need to maintain a state. You can just independently operate on separate chunks of data. So those kinds of algorithms are the most suitable for MapReduce. You just say no shuffle is needed, no reduce is needed, and then everything can be processed inside a map, right? But then not all the algorithms obviously follow this, right? Most interesting algorithms actually are not data parallel. I mean, I would say most algorithms are data parallel, but the most interesting algorithms are not data parallel, right? And so for those most interesting algorithms, MapReduce may not be a suitable implementation, right? But relaxing some constraints or relaxing constraints a little bit, and this we have seen a lot of times, getting to an approximate solution with more data parallel communication patterns, or rather complete lack of communication patterns, are acceptable when the data is large enough. I do not have exact the theory on that. I do not understand. I've heard about it from a lot of people who are actual practitioners of these machine learning algorithms on the Yahoo scale data, right? So that is why I think MapReduce became popular as a mechanism for implementing these machine learning algorithms inside of Yahoo, right? Yeah.
Can you give an example of a data parallel machine learning algorithm and an example of an interesting algorithm in machine learning that's not data parallel?
Sure. So anything that involves iterations which are more fine-grained iterations are the algorithms that I would call as not really data parallel. I mean, not map suitable for MapReduce, right? And this has come up again and again. Wherever iteration is there, and especially across iteration, you have to share state. That is where MapReduce actually sucks, right? So that's where, and that's why I'm saying there was something else here. Oops. Okay. All right. So the most appropriate, I mean, the way people basically took their machine learning algorithms and ported it over to run over MapReduce, I think the first candidate was where you could actually train multiple models completely independently on the same data, right? That's a given. That's basically just completely train independent models, independent modeling techniques, execute inside different mappers, and just produce those models, okay? You could train those in either in mappers or in reducers, right? So if you can basically fit in all the data inside, all the data inside a particular process, inside a single JVM, then you could train the models inside a reducer, right? Otherwise, what you could do is basically just split the amount of data that you are processing in each of the mappers, load it completely into memory, run your machine learning algorithms, produce a model, and then combine those models inside a reducer, right? So that's what the most of the distributed learning algorithms are programmed using MapReduce. It has also been used for ensemble training methods where you basically combine all the different kinds of models or train different models inside all the mappers, and then in reducer you combine all the models. Assumption is that the model is obviously going to be smaller than the amount of data that you are going to train it on. So the amount of data that is shuffled between the mappers and the reducers is going to be small, okay? So parallel training of multiple models is pretty simple. You basically assign a model ID for each of the model that you want to train. You load all this data into the data that you want to train your model on into each of the mappers. Each mapper is assigned to a particular model ID. It basically just trains the model and says, okay, sends it to the reducer. The reducer basically combines those models together, right? Distributed learning algorithms, on the other hand, when they are ported to MapReduce, they are more suitable for MapReduce if they are compute intensive per record, right? The reason being that if you are just reading the record and doing a very few amount of computations on each of those records, the overhead of spawning a particular map task on a remote machine and then establishing a connection to the HDFS and then reading all this data, which tends to be kind of slow because it is coming out of a disk, right? And again going into the disk for the shuffle phase. So unless you spend more compute cycles per record in an algorithm, those algorithms are not going to be sufficient for programming or efficient when programming using MapReduce. But what people have found is that MapReduce has been a pretty good fit for a lot of statistical query modeling techniques and a lot of machine learning algorithms or machine learning techniques that are commonly used apparently fit into this what we call as the SQM, which basically you are estimating a particular function. You ask an oracle, okay, how you do an estimate, and you basically ask an oracle how different I am from the actual solution. The oracle tells you something to move in a particular direction, and you basically repeat that process until you reach that particular estimate, right? So again, it involves iterations, but as long as your individual iteration grain size is large enough, you can program this using MapReduce, right? Yeah.
I think you covered it like earlier.
Sure.
When you showed streaming speed, I guess.
Yeah.
But still, like even with that streaming speed, what is the ratio of computation versus the streaming speed?
The streaming speed per disk is in practice you can expect to get about 50 megabytes per second, right? 50 megabyte per second, that basically is not the actual raw disk speed, but when you actually do the deserialization and finally get it to compute, you are getting about 20 megabytes per second, right? So now within a second, given the modern CPU, you can process up to a gigabyte, right, easily. And so that is what you need to take into account is basically if I am fetching this data at 20 megabytes per second, am I spending long enough time on that 20 megabytes data to justify just the launch overhead, right? When you take, say, a task launch overhead in Hadoop, the way it happens is that the task tracker wakes up once in a while, about every 3 seconds, goes to the job tracker and says, hey, give me something to do. right? So when you have tons of those, right, and there is a lot of number of tasks to be pending, that are pending to be executed are large, Hadoop job tracker being a single point, right, a single daemon, is actually doing a lot of calculations about, okay, which task is the most suitable to be run here, right? And that means the task scheduling overhead is actually gated by the task track, by the job tracker, right? Yeah.
SQL kind of algorithm.
Yeah.
I mean, so typically number of passes over the data you require
Yeah.
are very finite.
Yes.
It's of the order of 1, 2, or at max 3. I'm not saying more than that.
Correct, correct.
Right?
That's why it actually makes perfect sense, because so first of all, the number of iterations need to be small enough.
Right.
And the second thing is what state are you transferring between one iteration and another iteration? Right. But then there are, I have a whole slide on all these challenges in porting models to model training to machine learning, and some of the main bottlenecks for that is not only this, but every time you have to read the same data from the disk, that actually becomes another bottleneck there. Yeah, you have a question?
So I just wanted to add to the question was regarding machine learning algorithms that don't lend itself to MapReduce, right? So neural network training doesn't.
Yeah.
Because if you use stochastic gradient descent, because you have many iterations, like you're saying, you have
Second, your P2P communication.
you have a large number of network parameters.
Yeah.
That you have to pass. So when you use stochastic gradient descent and generalize, it doesn't lend itself to this sort of approach.
So it basically, MapReduce is very slow. That's what you're
Yes.
Yeah, because you have a lot of communication bottleneck by
Because
passing the gradients.
parameters are billions of them, right?
Yeah, exactly.
That's
You're
right.
computing this on a small amount of data, on a small many bits, so you're running many iterations.
Yeah, right. Yes, we.
But Tyler, that's exactly the point that I was making in my presentation. You've got to distinguish Hadoop from MapReduce. Hadoop faces problems. The main memory MapReduce. You're still using MapReduce. Everything is embedded and stays there, using data structures from one iteration to the other. So things that Mary just said do not apply.
Well, then we have to fit your whole thing into main memory, right? That's the main thing. Yes.
That's correct.
Yeah. Yeah.
But again, what Tana is talking about,
Yeah.
often it is the case the amount of data is not a lot. You can't fit into cluster memory.
Exactly.
The real issue is you've got to do a lot of computation.
Completely
That's
agree.
when you can use MapReduce, just not.
Completely agree. I think I should have given my agenda up front as to how I'm going with this story, which is basically saying, these are all the experiences of people that actually initially did MapReduce, machine learning in MapReduce, found it, to be severely lacking, and then moved on to other things. And those other things are the ones that I want to actually focus on. All right. Okay. So just to give you an example of the commonly used techniques in clustering, k-means clustering, you basically have k-centroids, and you have a bunch of data. You have to fit those into these key clusters. Obviously, each MapReduce job in here forms an individual iteration of this iterative process. Okay. In each of the iteration, you basically refine your solution a little bit more. Okay. And you need a control program which is outside of the framework of MapReduce to basically, first of all, initialize, then say, okay, now start one iteration, wait for that MapReduce job to finish, get the output from the MapReduce job, take that output of the MapReduce job and pass it on to the next. I mean, there will be some stopping criteria, but take that output of the job and pass it on to the next MapReduce job, etc. Right? So, okay, so for the map, in that case, and this is one iteration of that k-means clustering, is for the map, a bunch of data points xi, some initial estimate of the centroids, or the estimates that are derived from the previous iteration of the MapReduce job, and then you are basically finding out for each xi which centroid it is the closest to. That's pretty much what it is doing, marking that xi with that particular centroid and passing it on. Okay. And on the reduce side, now basically you have all these new xi's and the associated with the old centroids. Now you take refine this cluster by saying all these xi, I'm going to find what is the centroid for that. You update the centroid, that becomes the output of each iteration, that goes on to the next iteration, right? Okay. So you basically have endpoints and k as the clusters, and you have the distance computation is OD, especially where the complexity of OD, or the amount of computation that you do in order to compute this distance, if this is high, then this is a really good candidate for MapReduce. If this is very low, in that case each iteration finishes in a very short time. In that case, your job launching overhead, etc., will be really large, right? In that case, it's not a very good solution for or candidate for MapReduce. Well, so based on these initial experiences of really tackling large data and really having at least some go-to machine learning methods, maybe about 20 or so methods, right? A project was born again in the Apache Hadoop ecosystem called Apache Mahout. Apache Mahout has been around for almost 4 years now. I think most of the times it is used for recommendations engine with collaborative filterings and I think frequent item set mining as well is a very go-to method in Apache Mahout, right? The goal is not to make the most performant machine learning library, but rather the most scalable machine learning library, right? Given the amount of time that people put into developing these algorithms, at least my feeling is that most of the machine learning algorithm implementations will always be open source, right? Okay, I think it will come up. All right, no problem. So it will always be open source because people are going to make modifications and go tinkering around that, right? I haven't seen a single machine learning package, well, SAS aside, which basically you don't get the source for and you just straight away start programming, right? So having an open source scalable machine learning library was felt to be of utmost importance, and that's how Apache Mahout was done. I would say unfortunately there hasn't been a really consistent corporate sponsor for Apache Mahout who basically takes the ownership of Mahout and keeps it updated, easily deployable, easily operable, etc. And that is why the development on Apache Mahout has stalled a little bit, but at least still for somebody to get started with machine learning on MapReduce, I think Mahout actually provides a very good candidate, right? This is basically a list of all the algorithms in Mahout. Most of the times, as I said, the item-based recommendations is the one that I've seen most often being used inside of with Mahout. But again, the problem with Mahout are also the same things, right? Even if there are some sequential methods included in Mahout, the bulk of why people use Mahout is basically because it is its ability to handle large amounts of data and to use MapReduce, and therefore with the hype of Hadoop, you basically sit in the Hadoop ecosystem, you are golden, right? So that is why Mahout has benefited. But then the challenges with Mahout also remains. I mean, the same challenges with MapReduce remain with Mahout as well, is that MapReduce is optimized for really large data processing. I mean, most of the times you are filtering data, you are preparing your data for doing machine learning. After you have prepared your data, the data size becomes small. But in some cases, such as in Yahoo case, for example, in the case of Yahoo, we had something like 10 terabytes of web logs and click streams, etc., coming in every day. So if you had to analyze 13 months of data in order to determine people's click patterns over the years, right, that basically becomes a really large scale problem, and that's where MapReduce really succeeds or really excels, right? And again, as everybody said, MapReduce, the main problem is that iteration is not a fundamental concept in MapReduce, and most of the machine learning algorithms are iterative, and therefore the overheads of job launching each time you launch an iteration essentially takes over the entire efficiency that you have. Multiple scans is a huge issue because MapReduce does not support a good in-memory caching solution, so that you cannot have once you read the data, if it is going to be needed again for the next iterations, you cannot keep it somewhere close to you. You can, at most, you can keep it close to you on the disk, but even that disk is, on the local disk, but even that local disk is wiped out after your job finishes. Okay, so there is no real good way. We started a project called distributed cache, and that distributed cache feature is actually in the Hadoop mainline code, but on a multi-tenant cluster, since there is no, since this is distributed cache, not a resilient data set like Spark has, right? There is no way to guarantee that the next time my job comes in and my iteration starts, I will find that, so I won't be able to find that data in the cache. I will have to again read it from the disk. Okay. And obviously, as I referred to in the k-means example, you need a controller which is running outside of the MapReduce framework, typically on a client machine. Now, the client machine also has a chance to go down sometimes, so you have to do you have to implement the fault tolerance for the controllers if you have really long running iterations or long running iterative jobs inside a MapReduce cluster. Okay? And the controller has to do a bunch of things. Obviously, it has to coordinate all these multiple MapReduce jobs that you are running in each of these iterations, right? It has to implement a stopping criteria. It has to sequentially, and typically this controller will be sequential, running outside of the MapReduce cluster. So it has to, again, between the iterations, it has to go to HDFS, look at the last, the data that, or the output that the last MapReduce job produced, and sequentially determine whether to continue or not. So especially when your MapReduce job, which is doing an iteration, if it produces a large amount of data, in that case, obviously this sequential bottleneck comes into picture, right? All right. The task initialization overheads is something that that comes up again and again. So it's not only the task assignments and task scheduling on a particular machines, all the program files and all the library like side files, libraries, etc. that you have to you need in order to run your task, they have to be downloaded from the shared storage like HDFS, localized inside the task/ directory, and that actually adds a lot of overheads in the mapper and reducer task when they are started. And obviously, MapReduce is almost always shuffle bound. All the applications that I have seen so far in my life in MapReduce incur the maximum amount of overhead in data being shuffled from the mapper into onto the reducer. And the reason obviously being that in order to provide fault tolerance, the mappers has to write the data onto the disk, and reducer has to pick up this data from the disk, and typically the disk of a remote machine, transfer over the network. The network used to be a huge bottleneck earlier when we had only about a gigabit of bandwidth within our cluster. In that case, maybe about gigabit of bandwidth is maybe about 6 or maybe about 5 disks or something like that, or maybe even less. But now we are talking about 10 gigabits, and now the disk has again become the bottleneck, and network has sort of grown in bandwidth.
Does try to send a notification to get closer to the data? Is that something that
So map actually gets executed closer to where the data fragment already exists, like input split already exists. But there is no locality between the maps and reducers. The reducers scheduled completely independently. So the default scheduler in Hadoop has no notion of where to schedule a reduce closer to where the map is, right? So the reducer, and typically that is why the shuffle is almost always on the network, right? The map side efficiency comes from getting data local to the disk, but shuffle, there is no other option, right? Yeah.
Why you were saying this locality with the mapper? Because when I get the data, it's coming from some HDFS node into my input space. So where's the locality?
Well, the job scheduler in MapReduce basically places the map task close to where the split is. And the split corresponds to a HDFS data block, which is replicated on 3 machines, right? So the job scheduler has a choice of 3 machines in order to locate the map as close as possible.
Sure.
Yeah.
It's not the same EM. You still have to pay serialization, deserialization.
Oh, yes, absolutely. It's coming from the disk, so you are going to deserialize it anyway, right? Yeah. So if you look at the Spark work in RDDs, I think the one efficiency in RDD actually, or resilient data sets, actually comes from storing it in memory. But the second thing is actually this deserialization and serialization cost, because really the deserialization cost actually plays havoc on the CPUs. The 50 megabytes per second per disk output that input that I am getting, the reason that it is getting to 20 megabytes per second when it comes to my map method is because a lot of time is being spent in deserialization. Decompression also, but deserialization. Right? Okay. All right. There was another, in one of the talks, basically there was a notion of that unless all the maps finish, reducers cannot start, right? So you do not have this streaming kind of architecture, because now maps are already constantly producing these records which are transformed. They could immediately determine, okay, which reducer it needs to go to, and they could go to a reducer, and the reducer could immediately get started, right? There are a lot of reasons why this was actually done, and fault tolerance, and again giving reasonable semantics in order to what happens with the reduced task is restarted. For that reason, we cannot have maps streaming data directly to reducers, right? And that is why there is this blocking, this huge block introduced between the mappers and the reducers, right? Yeah.
So I have a
Mhm.
make them installable as binary. Where is the deserialization process there? I mean, it's basically binary data that you need to put in. Is Java that efficient?
That would be, so you would basically take at least the file format conversion you'll have to do, right? I mean, you'll have to fit it in some way in the file format, right? The sparse, are you actually storing it in binary?
Yeah, I mean, it's just one record. I mean, take compress parse row or something. It's
Right.
days of storage.
Right. If that is the case, then there is no deserialization.
So this is like average case 50 to 20.
Oh, most of the times people use the standard like text formats and then sequence file formats, and then these are readable again only. I mean, text formats are readable by multiple languages, but sequence file format, which is one of the very commonly used format in Hadoop, is readable only by Java. So what people have to do is basically store it in data structures which are Java friendly, right? And arrays, in particular multidimensional arrays, are not very Java friendly. Right? Sparse arrays you could represent by a column, row comma column comma value, but then when it actually gets in there, your sparse array, I mean, in what format it is going to be available to your sparse matrix computation library might be completely different. Right? Plus, this data is shared across multiple applications, which basically means that you have to choose the lowest common denominator in order to store this data, so that it is possible to be used in multiple languages and applications written in multiple languages and multiple frameworks. So that's another thing. Lots of reasons, especially when it comes to multi-tenant. I mean, this is okay. I'll go on a rant here, but this is the difference, I think, is between doing research to produce a paper versus maintaining a huge system which is going to be used in completely unpredictable ways by people coming from all walks of life and with completely different aims and producing completely different outputs, right? And that is why you have to take this. I mean, we could have optimized. I mean, it's not that there is no room for optimization. We could have optimized if we knew what use case to optimize for, right? Since this was a completely multi-tenant cluster, hundreds or thousands of different use cases, we had to resort to a lowest common denominator, and that's where all the inefficiencies. I mean, most of the inefficiencies come from there. All right. So, in order to implement iterative algorithms in MapReduce, the only shared location that you have to share the state among different iterations in HDF is HDFS, right? So the overhead per iteration, as we talked about, job setup is the big overload. Data loading, again and again you have to scan the source data, and the whole disk I/O involved in sharing the state in the distributed system and getting it back onto the next mappers, right? Obviously, the world was not just following MapReduce blindly or follow Yahoo or Facebook blindly. They were actually suggesting enhancements, right? A lot of these enhancements were basically, let's look at one aspect of MapReduce and try to fix that, right? That's basically, I mean, the inefficiencies coming in MapReduce, and let's try to fix that, right? Basically, over the last 4 years, we have actually seen a lot of papers being published. The worker aggregator framework actually came from Marcus Weimer. Hadoop came from University of Washington, Magda. MapReduce Online came from Yahoo. There is another paper called MapReduce. Spark came from Berkeley. A bunch of those, right? They try to modify the MapReduce working model while trying to, first of all, keep the connectivity with HDFS, because that's where your data is. If you have a machine learning framework that does not connect some way with the Hadoop distributed file system, that framework has very low chance of succeeding, right? That's sort of the reality accepted by the marketplace. So they try to keep that. They try to keep some sort of fault tolerance aspects, right? Not all these enhancements that are proposed actually have the same fault tolerance property as the rest of MapReduce. So I'm going to briefly touch on only those two, only the two that I found being actually used in practice. So Marcus Weimer's and Tyson Condi's work on worker aggregator basically just reduces the shuffle phase completely, right? So just launches a MapReduce job, a bunch of map tasks are launched, and these map tasks essentially are doing the iterations in each of these tasks. At the end of each iteration, each map task talks to an aggregator, which is just sitting there, right, as a daemon. It talks to an aggregator, deposits a state. The aggregator waits for all the P1 to Pn map task iteration outputs to get in there, does some combination of that, and actually communicates the result back to all the mappers, and then they start the second iteration. Right? The final output then is written through the aggregate, and the stopping criteria, etc., is actually implemented in the aggregate. Right? So what it gets rid of is basically, first of all, the state being shared across through HDFS after each iteration. So that's one thing that it gets rid of. The second thing that it gets rid of is actually having to schedule this job again and again and again, part of every iteration. The map tasks are just staying there. Okay? Yeah, I already stated that. All right. The second one, which actually I liked a lot personally when I actually read the paper. I do not know whether it has been actually used in production at all. At least I like the name a lot. Right? It's called Hadoop. So it's basically Hadoop optimized for iterative computation. It actually adds new APIs in order to be able to program these iterative Hadoop computations or iterative machine learning applications, the algorithms, very nicely. Okay, so the second big part of Hadoop actually is the loop-aware task scheduling. Right, so it knows that the Hadoop program typically goes through a bunch of different loops. Right, and in order to provide fault tolerance, the tasks have to finish and then have to restart again. Right, so those two things are seemingly incompatible, and they actually try to combine that by making the scheduler aware that this task is going to be again executed in a short amount of time. So probably I should reserve that node for this task that is coming. Right, that reduces the utilization a little bit, obviously, because while that task is not running and we are waiting for the controller to launch the task again, we are spending some time on the node which without doing anything. Right, but at least gives sort of a notion of efficiency in scheduling these iterations again and again on the same amount of nodes. Right. The second thing that it does is, since there is a high probability that the same instance of the task in the next iteration is going to be started on the same machine in a short amount of time, now I can actually use the local machine, either memory or the disk, as a cache in order to share this data across these different iterations. I do not have to go back to HDFS and start fetching all this data again. I can actually store it on my local disk. And if I have SSDs or anything like that on my local disk, or if I have large enough memory in which the data that is being written to the local disk is actually buffered before the next task iteration comes in, so that I can read it from memory and at a much higher bandwidth. So the amount of time that it takes in order to read the next data for the next iteration is going to be really small.
So basically,
yeah.
Can it be used, for instance, in this, we know that information barrier can introduce this cost where you're waiting for the slowest machine, right?
Right.
So are you talking about the case where the second user, where let's say the first user's code is waiting for the next iteration to happen,
Right.
and then 80% of the machines are waiting, and
Yeah.
then the next user's next iteration is being executed by those 80%.
So I mean, let's just think about one single job, right? I mean, so this is being optimized for one single job that is coming in again and again as part of these different iterations. That's pretty much what it is, right? Now, given the way MapReduce divides the resources among different users using either fair scheduler or capacity schedulers, multiple users' jobs are going to be cascading anyway. Right, so the Hadoop in particular does not make any modifications to that part. It only makes modification to a single job scheduling problem, right? But now that the whole thing is now that since the scheduler itself is loop aware, it has it can take the liberty of caching this data and making sure that it is going to be available. Again, this is the cache, right? This is, I mean, if somehow that machine goes down or the cache somehow gets wiped out, you can again read this data. So only the loop invariant data in these jobs, those are cached. Okay, and this is the same principle that is used in RDDs, right? I mean, RDDs, I think in Spark, RDDs came much later than the Hadoop work, but Hadoop essentially had this notion much earlier.
So this caching is done at the level of deserialized data or Java data structure?
This is actually Java serialized data again. It actually reserializes that data. The only thing that it gets rid of is not having to read it from HDFS again. So trying to contact the name node and then going to the data node and fetching it, Rather than that, I'm just going to keep it in my local disk. And when I keep it on local disk, I'm again going to serialize it. And since this is taken care by the framework, it does it in the local, the least common denominator way. Yeah.
Then we have to keep it as Java data structure, but you don't support this.
Right. Yeah.
So the data here is still serialized, but not deserialized.
So, no. So once you deserialize, you get it into memory, right? What Hadoop is trying to do is basically pushes it again into the local disk rather than HDFS. When you have to push it onto the local disk, they are again reserializing it, right? So that's one inefficiency that they did not get rid of. The RDDs on the other case in Spark, they got rid of that, or at least have plans to get rid of that, right? Okay, so I think we have talked a lot about Spark. I'm going to switch away from Spark. But what we have seen now happening is that since all these deficiencies of MapReduce were brought forth by the research community and even by the industrial community, right? We had already started rethinking about the Hadoop architecture itself, right? So the whole notion of MapReduce being the only programming paradigm that runs on top of Hadoop was already going away, right? In one of these talks, I've actually heard somebody say that Hadoop earlier used to be something like a regular phone in which you used to just only be able to make calls. Now Hadoop has become sort of the smartphones. Now actually you can develop apps on top of it. I mean, so it has become sort of a chest rather than being a single tool, right? So all that has been done is that the job tracker and the task tracker framework, which allowed MapReduce to be run on top of HDFS, that has been now refactored into a cluster resource management versus MapReduce. Okay, and since the cluster resource management piece, which is now called YARN, has been completely modularly separated out, now we can have multiple different programming paradigms. All that they need to do is talk to YARN in order to gather resources, and after that they essentially take over the cluster, right? So because of that, what has happened is that already we have seen a lot of other programming paradigms or different kinds of services, I would say, being provisioned on top of Hadoop or on top of YARN now. So now Hadoop has truly become sort of a smartphone of data processing frameworks. Again, for the lack of time, I'm not going into the deep architecture discussion. So as I said, the job tracker and the task trackers have now been sort of modularly separated out. Instead of a job tracker, now there is a resource manager which does not know anything about MapReduce. All that you ask the resource manager is basically give me a container that can have 2 gigs of data, 1 physical core, and some X gigabits of bandwidth. That's pretty much it, or something like that, right? And then individual nodes run node manager. Again, node manager knows nothing about MapReduce. Node manager basically knows, okay, these are the containers that are living on my machine. Are these containers alive or dead? That's pretty much it, right? So with this refactoring, now MapReduce becomes an application that runs inside of this framework. So the notion, the role of the job tracker in the earlier Hadoop 1.0 is now simply an application launcher and application scheduler. That's pretty much what it is now. Okay. So taking advantage of this, we have basically seen the 40-year-old SQL language to actually make a huge comeback onto Hadoop, right, in its MPP form. So what we have seen in the last year in the Hadoop ecosystem is basically a resurgence of SQL-on-Hadoop offerings. Obviously, Pivotal, my company, was one of the first ones to launch something called HAWQ, which was the Greenplum database running on top of Hadoop. But we have seen Cloudera, Facebook, MapR with their Apache Drill, Hortonworks, all these companies actually clamoring with their own SQL-on-Hadoop solution. The way a SQL-on-Hadoop solution typically works is that SQL can be implemented very nicely with this MapReduce-like programming model, where you have a gang of processes which are basically communicating in a shuffle-like manner across different stages, right? And the only difference with MapReduce is that instead of storing the data on the disk between those two gangs and that is materializing this data, you basically transfer it over the network, right? So whoever has the most efficient interconnect in the MPP SQL basically wins, right? So that's basically where we are going. So it runs very similar to what a typical MapReduce program runs. So instead of a map task and a reduce task, everything is basically a faceless. It's called a segment or something like that in case of a Impala, I think it is called a partition. And then these basically are scheduled as close as possible to the data, which is right on the machine that is running the data node. So they are all reading in local data. And then once they process data in some way, they are actually transferring this over the interconnect, which is rather than over the network rather than pushing it onto the disk. And this is again sort of getting future proof because the network speeds are increasing much more than the disk speeds, right? So again, the network bottlenecks are getting lesser and lesser in large scale commodity clusters. All right. Just to give you a performance numbers, this is preliminary benchmarks of all the different, I mean, I'm just comparing the two of them. Hive is basically getting modified and into a project called Stinger, just getting more and more SQL in that, so I think it makes sense to compare these MPP SQL databases with Hive. If you can see, since Hive uses MapReduce underneath today, it takes a long amount of time. This is the 22 TPCH queries, and the in-memory transfer based or network transfer based MPP databases running on top of Hadoop are actually significantly better, sometimes 50 to 100 times better than that, right? Nothing surprising there. Okay, but what these new MPP SQL databases on top of Hadoop enable is this whole notion of in-database analytics, right? Joey Hellerstein and a bunch of people from Greenplum and University of Florida and University of Wisconsin, Chris Ray from University of Wisconsin, they have been working on this open source platform called, or open source machine learning libraries called MADLib, that actually are the set of user-defined functions that implement various machine learning algorithms inside of the database, right? So the database executor, the database execution engine is actually running close to where the data is, and it is actually running all these machine learning UDFs also inside of that. That is the whole idea of MADLib. And now with MPP databases making a comeback in the Hadoop infrastructure, now the HAWQ, the kinds of HAWQ database engines running on top of Hadoop, we can actually now support MADLib running inside of that, right? So taking a big picture as to where Hadoop is going, basically you can see that the MADLib algorithms are sitting right inside of the HAWQ advanced database services there. Impala also has, I mean, this is not a marketing talk, Cloudera's Impala has also started supporting MADLib inside of that. A bunch of different functions are already given there. The way to access MADLib is basically through a SQL interface. So for people who are used to SQL, it's very natural for them. There are some people who are not used to SQL, and therefore, going into the select statement and doing k-means inside of select probably does not make sense a lot, right? But for people who are mainly business analysts and want to sort of, do some machine learning, I think this is a solution for these guys, right? Yeah. No, they have been told to do this. They read the manual and they are being told to do this, and they basically try it out, right? So that's basically the solution for them. Yeah, sure. Yeah, let's try to wrap it up. Okay. Just maybe a last example that I will give is basically how to combine these MPP SQL engines and R. Okay. Earlier, what we used to do is basically R used to get the data from the database using an ODBC connection, load it into a data frame inside of R's memory, and then do the computation, right? What Pivotal R, and this Pivotal R is again another open source project, it's actually available on CRAN, you can download it from there, and it actually works with MADLib. So what it does is the interface remains the R client, we override the db.object inside of R, and basically do this lazy evaluation of R functions using and doing in database analytics, right? So the execution of the R application is, or most of the parts of R which is actually dealing with, or R programs that is dealing with the data, is actually happening inside of the database. So that's the big difference between regular R and this way of doing things, okay? And the parallelism, which is how many shards is this data split into, how do I access these in parallel, how do I implement this particular algorithm in parallel, that is all that is all handled by Pivotal R. Currently, it does not support the full R functionality. It only supports a few of them, and I have a slide on that. But the simplest way of doing this is basically, okay, instead of data.frame, I will say db.data.frame, give it a table, T1, and then once that happens, then I can actually access all its columns and all the types inside of that database directly in R functions. Okay. So it's also a wrapper for all the MADLib or some of the MADLib functionality, and then it also supports a bunch of other functions or a bunch of other operators in R already. Okay, and most of these are implemented in parallel. Okay, just to give you a architecture of this, this is basically how it is implemented. We derive from db.objects. Whenever some operation needs to be done on this db.data.frame, through our query, we basically actually go and do this in the using the MADLib wrapper functions, etc. inside the database, right? Not a lot of interesting thing if you are coming from the learning background rather than systems background, right? So the good part about this is that all the data stays in the database, right? The R objects are merely pointing to that. They are not actually loading this data into memory. So the memory limitation that, okay, if you have a terabyte worth of database out there, loading all that terabytes in memory for a sequential R machine and then doing computations there, you rather push those computations inside the parallel database machine itself, right? That is what is basically happening. And obviously the database talks SQL, so from R, somehow these SQL statements have to be generated in order to execute MADLib or other parallel machine learning algorithms inside the database. So all that is taken care by the Pivotal R client. Only the strings, that is the SQL statements, and the results returned by the SQL statements, those are the only things that are being communicated between R and the database. Okay, so that's where we are going. I have a few more slides, and actually just let me mention one thing. All these new, Hadoop clearly is moving beyond MapReduce, right? And since all the data is already there, if your computations are moving to the data, then your programming frameworks will be moving to Hadoop. That's basically what I'm saying, what I'm hoping will happen. And I think we have already seen a lot of evidence by that. We have actually seen graph processing, continuous event processing like streaming computations like Storm, even long-running services like HBase that are required for serving real-time clients. That's being ported on top of Yarn. And a personal favorite of mine, because that combines my first 10 years of HPC and next 10 years of Hadoop into one, which I cleverly call Hamster, is actually Hadoop and MPI on the same cluster. It's actually running MPI jobs by scheduling Yarn containers and then doing OpenMPI computations inside of there. So that's happening. That's coming pretty soon. In February, we are going to make it GA. And because of Hamster, which is MPI on top of Hadoop, we get GraphLab for free, because GraphLab uses MPI as its communication library and HDFS interfaces or HDFS data interfaces. So since GraphLab computations run directly on top of MPI, with Hamster we get GraphLab for free. So that's all coming in February. All right, enough. Thanks. Yeah. Sorry, proto buffer? So protocol buffers is basically a serialization and deserialization mechanism. We already, a lot of people already support that. There are proto files, etc. for MapReduce. And for HAWQ, we have a service called Pivotal Extension Framework that understands protocol buffers. The second one was? Oh, distributed hash tables. Distributed hash tables, actually, there was one big block diagram that in that block diagram that I skipped, which was called Gemfire XD. Gemfire XD is in-memory data cache, which is sort of a key value pair, or you can use HBase as a distributed hash table, right? Yeah. HBase is essentially a distributed hash table. Yeah.
So you talked about pivotal R.
Yeah.
When you write R statements,
Yeah.
You convert them to SQL queries to get the output.
Correct.
You create new tables in the database, or they're out?
So there could be temporary tables. There could be temporary tables that are created, but only during the execution of that program, right? So for example, in k-means, all these centroids, etc., that are being stored are stored in a single line temporary table, right? And we have enough intelligence in there in the database itself to sort of do garbage cleaning and clear those temporary tables. Yep. Right? Thanks a lot.